Section 3.2, Graphing Equations. We will learn how to graph an equation by point plotting and how to use symmetry in plotting the equations and graphing the equations. Now let's start with the equations in two variables. So an equation in two variables mean an equation in terms of x and y. So it has two variables. So it's most of the time x and y. So for example, y is equal to x plus 1, or y equal to x squared, or 2x minus 3y equal to 4. Now let's talk about what is a solution of an equation with two variables. So for example, look at this equation. In this equation, 1, 3 is a solution. So it's 1 is standing for x, y is 3 is standing for y. So as you see, the ordered pairs, okay, the solutions of such equations are ordered pairs. So y1, 3 is a solution, because when you put here x for 1, so we get 2 times 1 plus 1 equal to 3. So this is true. So substituting x equal to 1 and y equal to 3 here, it gives a true equality. So we say it's a solution. So what are the, can we find other solutions? So for example, what about 0 and 1? So 0, 1 is another solution, for y equal to 2x plus 1, because when you put 0, you got 1 equal to 2 times 0 plus 1. So when you plug x here and plug, this is not true. If you plug x here and if you put here 1, this is true. So it satisfies the equation. So we say it's another solution for y equal to 2x plus 1. Now, can we find more? Yes, we can find more. Indeed, the equations in two variables generally have infinitely many solutions. So most equations in two variables, they have infinitely many ordered pairs as solutions. So the solutions are here ordered pairs. One is for x, the other one is for y. So let's look at this example. Find the ordered pairs in the form of B12 that are solutions of the equation y equal to x squared minus 4. So if B12 is a solution of this equation, then when you substitute B for x and 12 for y, it has to satisfy the equality. So for example, when you plug it for x, for y, you have to have this y is 12, and for x we have b, so b squared equal to b squared minus 4. So 12 is equal to b squared minus 4. Then we will solve it for b. Okay, when you send it to the other side and solve it, you will get two values of b. So we can say for these two values, 4 and minus 4, these two pairs are the solutions of the equation. Now let's look at this example here. Try and check exercise. Find the solution. So for each equation, find at least two ordered pairs that are solutions. So we will find some solutions. We will try to find the ordered pairs, two numbers. We want to find two numbers here for x and for y, and they will make the equation true. So how about making 0 and 4? So if I take 0, if I take 4, is it true? Like 4, is it equal to minus 0 plus 4? Yes, so 0, 4 is a solution. What about, most of the time we plug the first one and we get the y value. For example, you put 1 here for x you put 1. So if you want to, okay, most of the time we say x equal to 1, then find the y value correspondingly. So you say it's 1, so minus 1 plus 4 is equal to 3. So you say, let's take 3, 1, 3. So 1, 3 is a solution. And you can also pick a y value, for example, with 0 here, and then x should be 4, so 0 equal to minus 4 plus 4, yes. So if you take x equal to 4, then it's okay. So you take 0, 4. So basically you can find the other component by using the other component, like one component from the other you can find. Now let's do the same thing here. For example, take x equal to 0. So what do you get? Y equal to 5. Okay, 0, 5 satisfies the equation. And what about x? Putting x equal to 1, then you got 1, 3, because y equal to 3. So if x is 1, then you put it here, then you got 3. So what? 1, 3. So the idea is you can use one of the components to get the other one. Now, here comes the fundamental principle of analytic geometry. The analytic geometry, the very important thing is this. A point AB lies on the graph of an equation if AB is the solution of the equation. So what does that mean? This means it's about the graph of an equation. So the graph of an equation is the set of the collection of or set of all solutions of the equation. So maybe the best wording will be the graph of an equation is the plotting the set, the plotting of the set of the all equations, plotting of all solutions. Now you will see what I mean. So for example, so look at here. This is the graph of y equal to x squared. So this is, okay, what does this mean? When you take any point here, take the x component and y component, like 3 over 2, 9 over 2, 9 over 4. When you put them here, they satisfy the equation, right? So it's a solution. It's a solution of the equation. And then when you locate them in the Cartesian coordinate system, it gives a point on the graph. So the graph, as you see, all these points on the graph, all these ordered pairs, okay, all these are ordered pairs on the graph are solutions of x squared equal to y. So when we give you the graph, we give you all the solutions on the graph. Or if we ask you the graph, so graph is asked, so you find the solutions and put them in the graph. Or we give you the graph, you give us the solutions. Like you can pick the points here and you say these are the solutions. Or you can find the solutions and put them in the graph. We put them in the Cartesian coordinate system, and it will give you the graph. So graph means the set of solutions, and set of solutions means the graph. Determine whether a given point is on the graph or not. So we will try to see if this ordered pair or point, like you can say point or ordered pair, they're both same in our context, because you can take this one as an ordered pair. Whether determine the point 1 minus 2 is on the graph of x squared minus 2y equal to minus 6. Now, how can you check? So by using the analytic geometry principle. So AB is a solution of the equation. Means AB, the point AB is on the graph of the solution. On the graph of the equation. Now, we are checking, we will check if this ordered pair is a solution or not. So basically it's asking this. So it's asking this question. Now, let's see. You substitute them in the formula, in the equation, and you check. So you see here, we'll put here 1 squared minus 2 times minus 2. Is it equal to minus 6? So as you see here, this makes 5. 5 is not equal to minus 6. So what do we say? No, it's not a solution. So this here, you can say 1 minus 2 is not a solution of the equation. So it's not on the graph of the equation. The intercepts of graph. We will see two types of intercepts, like x-intercept and y-intercept. The x-intercept of a graph is the x-coordinate of a point where the graph crosses the x-axis. So, for example, in this picture here, the graph is intersecting the x-axis at the point A. So A is an x-intercept. So can there be more x-intercepts? Yes, for example here. So we have this x-intercept 1, second one, the third one, the fourth one, fifth one. So there might be many x-intercepts, and also there might not be one. For example, look at here. So you see there is no intersection with the x-axis, so no intercept here, no x-intercept. So there is no x-intercept here for this graph. So there might be intercept, x-intercept, or not, or maybe more than one. Now for the y-intercept is same, except we will check the intersection at the y-axis here, so on the y-axis. So y, so you look at the graph, so it cuts the point, like it cuts the y-axis, or it intersects the x-axis at B. So we say B is a y-intercept. Again, we might have, depending on the equation, we might have 2 or 3 intersections, y-intercepts, or there might not be a y-intercept. So if your graph is something like this, it might be a closed graph. So then there is no y-intercept, no y-intercept here. Why? Because it's not touching the y-axis, you see. It's not intersecting the y-axis. Now we will learn how to find them mathematically. So because when we give an intersection, when we give an equation, the equation will have a graph. So, and we will check if the graph has an intercept. Now, the intercept of an equation or the intercepts of its graph, for sure. x is an x-intercept of an equation is a value of x when y equal to 0. So for example, what's the x-intercept of this equation or its graph? We set y equal to 0 and solve for x. So for example, you put here 0, you got x squared minus 1, and then you got x squared equal to 1, and then you got x equal to plus and x equal to minus 1. So we say minus 1. Okay, so we say 1 and minus 1 are the x-intercepts of this equation or the graph of this equation. Now, y-intercept of an equation is the value of y when x is equal to 0. So look at here again. In this case, you want to get the y-intercepts, you set x equal to 0 and then solve for y. So it means like you write here 0 squared minus 1. So it turns out y should be minus 1. So you say minus 1 is the y-intercept. The y-intercept of this equation is minus 1. And some equations doesn't have x or y-intercept. If you use this procedure, setting y equal to 0 or x equal to 0, some equations will not give a solution for the other variables. So for example, look at here. You put here 0. What do you get? 0. So if you put here x equal to 0, you will get 4 squared plus y plus 5 squared is equal to 1. And when you try to calculate, you will get y plus 5 squared is equal to minus 15. And so there is no solution for it, no real solution. So there is no real solution means no y-intercept. And you can also solve the same thing for y. Solve it for y. So say y equal to 0 and solve for x. So then you will get x plus 4 squared is equal to, plus 0 plus 5 squared is equal to 1. And when you solve this one, you will get x plus 4 squared is equal to minus 24. So as you see, it's a square and it's minus, so there is no real root. No real root again. You can solve the equation, but you will get complex roots. So no real root means no x-intercept here. So for both, with this example, we see sometimes some equations doesn't have intercept. X, no intercept, no x and no y-intercept. Okay, let's look at this example. Find the point that the graph intersects the x-axis and the y-axis. So you don't need to graph this one. So it's basically asking the intersect, asking x-intersect, and y-intersect. Now the procedure is straightforward. Just if you are looking for the x-axis, so to find the x-intercept, you set y equal to 0 and then you solve for x. So these are giving you the x-intercepts. Now for the y-intercept, to find the y-intercepts, you set x equal to 0 and you plug it in the equation and you find the y-intercept. So you say y-intercept, these are the x-intercepts, but it's asking the point. So when it says find the point, so you mean the ordered pairs. So we want the coordinates of the points. So what can you see here is this x-intercepts are where it's at 3 and minus 3. somehow the graph is cutting them or intersecting them. So which points are they? I mean, this is corresponding to which point? -3, 0. And this point is corresponding to 3, 0. And when you look at here, it says y-intercept is -9. So there's this -9 is somewhere here. So this the graph is cutting this one at this point, intersecting the y-axis here at this point. So what point is this? As an ordered pair, it will be 0. The x component will be 0, and y component will be -9. So this point form the coordinate will be 0 and -9. So we say that the ordered pairs corresponding to the intersection or the intercepts are here, these 3, 0, -3, 0, and 0, -9. Okay, let's do the same thing for this try and check problem. For each equation, find the x-intercept and the y-intercept of its graph, if there is. If any means if there is. If it is possible. Okay. For x-intercept, we set y equal to 0, and you plug it in the equation, so it makes 0 is equal to x squared plus 4, and then you try to solve this one, you get -4. So if you try to get one, you will see this is -2 plus -2i, you see? So there is no real root here, no real root, no real solution for x. So you say then there is no x-intercept. There is no x-intercept of this graph. So for the y-intercept, we do the same thing. I mean, almost same thing, but this time for y. So for the y-intercept, set x equal to 0, and this will be y equal to 0 squared plus 4, and y equal to 4. So you say 4 is the y-intercept of the equation, or its graph. Equation or its graph. So when we say an equation, it corresponds to a graph, right? The set of solutions will correspond to a graph. So you can say its graph or the equation itself. Graphing an equation by point plotting. Now, we didn't talk about how to make the graph of an equation, but we said the x-intercept and y, how to find the x-intercept, y-intercept of the graph, and how to know if a point is on the graph. Now we'll learn how to make the steps. Okay, what are the steps for graphing an equation by point plotting? The first thing is, if there is intercepts, so if there are intercepts, find them. I mean, you will try to find the intercept, and you will find more ordered pairs on the graph. So it means you are looking for the other solutions. Okay, just check if there are more solutions. I mean, not check, but find other solutions. For the equation. I mean, you can make a table when doing this. Generally, we do a table. We make a table, and then plot the ordered pairs. Like from step 1, step 2, you have some intercepts and some points here. So you can put the intercepts as the points also, and you put them here, like these, and here, for example, like these, and you connect them. Then it gives you the graph. Okay, we will see them. Now look at here. Okay, we always keep in mind that a point xy, the ordered pair, lies on the graph of a point, of an equation, if and only if its coordinates satisfy the equation. So it's a solution. It should be xy, x comma y should be a solution for this equation. Now let's graph the equation. This example graph the equation y is equal to x squared minus 4. Now let's go for the x-intercept and y-intercept. So for y-intercept, you set x equal to 0, and for x-intercept, you set y equal to 0. Then for x equal to 0, so you substitute x equal to 0 for this part in here, and you got y equal to 0 squared minus 4. So y equal to minus 4 is the y-intercept. And then you do the same thing for y. So you put y equal to 0 and find the solutions for x. So you got two values for x. So you say the x-intercepts are plus 2 minus 2. So you can put them in, you can list them as ordered pairs here. It's minus 4, the y-intercept is minus 4, it's here. So you say it's this point. And 2 and minus 2 are here, and they correspond to these points. If it is on the y-axis, x is 0. If it is on the x-axis, y is always 0. We found the intercepts, and we want to find more points. So for example, like this one here, 3, 5, negative 3, 5. Okay, now how do we come up with these? So I will show you. Generally, we take a value for x and put it here. So assume you don't know this one yet. Okay, you got 5, so you say it's 5 here. Then do the same thing. You assume you don't know this one. Put it here. Minus 3 squared. It gives you 5 again. Then you come back to here again. So they turn out to be same value. They don't have to be same, but here it turned out to be they turn out to be same. Now we have the other points. We have 3 points coming from the intercepts and 2 more points. If you want to do more, you can do, like you can put here 1. Okay, what will happen? X squared minus 4. Just put here 1. So what happens? 1 squared minus 4. It will be minus 3. So you can say here it's minus 3. And then another point will be 1 minus 3. Okay, you can do more. Like if you want more detailed graph, you can pick more points. The computer softwares, the graphing softwares, they take maybe like thousands or more points and maybe million points to make a good graph. Yes, the next step is we will put them in we will plot them. We'll plot them. It's when you plot them on the Cartesian coordinate system, you have this one here, and you have this one here, and you have this one here. And what about these? 3, 5. It's here. Negative 3, 5. It's here. If you want to get some extra, it's 1 minus 3 is somewhere here, I guess. So you can try this 1 and minus 3. And then when you put them together, all together, then you can combine. We can connect them with a smooth curve. Then it gives you the graph of y equal to x squared minus 9. Now let's graph the equation y equal to square root x minus 3. Now let's go with the step 1, the intercepts. Now for y-intercept, set x equal to 0. So when you set x equal to 0, you got y equal to square root 0 minus 3. So y is equal to negative square root 3, which makes square root 3i. So this is not real. So you say no intercept, no y-intercept here. Okay, I'm sorry, this happened. Y-intercept. No intercept. Now for x-intercept, set y equal to 0 and try to find the solution 0 equal to square root x minus 3, and then you can take the square of both sides. You will end up with x equal to 3. So you can take the square and you know, be careful about the fake solution, but this is 3. This doesn't make, you know, fake solution. You see 0 equal to 0. Anyway, so you say this 0 at 3. So 3 is the x-intercept here. 3, let's go to 3 here. So this is 3. So the graph is somehow passing through this point. Anyway, let's choose the other points. This is the x-intercept only. And what about the other points? Well, let's make a graph, like, a table like this. For example, how about putting 1? So what do you get? Y equal to square root 1 minus 3. Oh, okay, this is bad because this is not real. So it seems for x equal to 1, there is no value for y. So put 2 here, same issue. 3, we got 0, and we already did that here. 3, 0 is here. And then you can put 4. Yeah, it's 4, 1. So this is 4, 1, right? Where is 4, 1? It's 4, 1 is here. 4, 1. This is another point. And now take other points. Let's say 5, or we can pick some more like 7. So this both gives you 7, 2. This is another point here. 5 is here, 6 here, 7. 2. And then, so we have these points here. And how about taking 10? Square root 7. This has to be something like 2.6 or 7 maybe. Okay, so we can check it with the calculator, but it will be like here 10. When it is 10, it will be 2 points like here, 2.7. .6. So we have these points. So we connect these points and we get the graph. So for this side, there is no point. There's no point on this side because of here. You know, before 3, 1, and 2, we checked and there we couldn't find any point here, so there's no point here. So some equations, they don't have points everywhere, so you might not find points, everywhere for all curves. Now, reflections of a point through the axis. Now we will learn 3 types of reflections here. One reflection is about the y-axis. This is pretty easy. For example, if you have this equation, this point here, and if you want to find the reflection of y-axis, find the y-axis and take its reflection. So it's this point. So if it is A and B, now this makes minus AB. So you see the level B is same, but here if it is minus 2, that will be 2. So you see here this 2 is minus 2. You see? This is A, and this is minus A. So the formula still works. This might be minus, this will be plus. If it is plus, then this will be minus. You know, then the next thing we will do is the reflection of a point through the x-axis. This is the x-axis, so you're taking the reflection through the x-axis, so you get this one. Like here, A is same, so A is same here, and then we have the same thing, A. But when we talk about B, if it is B, it has to be here minus B, so you say it's minus B. So again, if you use these points here, for example, this is 2, minus 2, 3. You got again minus 2, but this time it will be minus 3. You see, it become minus. Now the reflection of a point through the origin. The origin, is this point is called the origin. So look at here, AB. Now you're looking at, you're drawing a line, and this is a line segment. Okay, this is a line, straight line. Now then you go up to here, this distance, and if you go on the direction of the same line but the same distance, you will get the reflection. What's the reflection of AB? It's minus A minus B. You can check it. Look here, you have minus 2 and 3. What do we have here? 2 and minus 3. So you see here, this 2 is, if you apply the formula here, it will be, this is A, let's say this is B. What is minus A? It's minus 2, which is plus 2. And if B is 3, then what is minus B? It's 3, so it's here. So regardless of A and B, no matter what their sign are, the formula works. You have negative, positive, or positive, negative, doesn't matter. The formula is this. So you have to learn about these, okay? Now let's look at these. So plot the point 2, negative 3, and its reflections through the y-axis and the x-axis and the origin. So 2 Okay, where is 2, -3? Okay, 2, -3 is here. This is our point. Its reflection through the y-axis. Reflection through the y-axis, so it has to be here. So the same distance, it goes up to here, which is -2, -3. And the x-axis, the reflection around the x-axis, I mean, you go this way and go this way here. This is 3 units and this is 3 units. And now we end up with this here, 2, 3. And through the origin, so you have to go, okay, how to get the origin? You can do this way. How many units you went here? 3 units. You go 3 units up. Then here you go 2 units. You take both reflections separately and connect them here. Or I will say take the reflection with respect to x-axis and then take the reflection with respect to y-axis. So first take reflection through x and then y. So you will get this one here. According to x-axis through x-axis and through y-axis, or you will get the point C. This is our point and its reflection here. And when you look at the coordinates, it's -2, 3. So this is -3, 2. And also you can use the previous information like AB. It's a reflection through the origin. Is -A minus B. So this is 2, -3. So its reflection here will be -2 plus 3 because this will be -3. So it's this one, you see? Now, symmetries of graphs. We will learn 3 types of symmetries of the graphs. So this is the last topic we will learn. Symmetry with respect to x-axis and the symmetry with respect to y-axis and the symmetry with respect to origin. Now, let's look at what does symmetric with respect to y mean. Okay, a graph is symmetric with respect to y-axis if the reflection of any point on the graph through y-axis lies on the same graph. So it means, okay, it has, okay, if it is y-axis here, this is y-axis, then if the graph is symmetric with respect to y-axis, it means if you take any point, its reflection through the y-axis will be also on the graph. Like take this one and take this one, take this one and take this one. So you will see its reflection that does, okay, y is the mirror here, Aina. You know, then you see the reflection here. So this is, if we have the reflection of a curve is also, it's a part of the curve, then you say it's symmetric with respect to y-axis. So, or sometimes we can say it, if you fold this side to the other side, so it overlaps, then it's symmetric with respect to y-axis. Now, a graph is symmetric with respect to x-axis if the reflection with respect to x-axis is same. I mean, it's on the graphs. Like, take this one, its reflection with respect to x-axis, it's here again, so it's on the graph. And also, you can say if you fold this one, fold on the other leg, fold on this leg, this one, so they will overlap. So symmetric, so this is with respect to x, so x, same behavior here, same behavior. It's like this is like a mirror here. You did the same thing on the other side of the mirror. When you look at the mirror, you see yourself in the same distance. Now, with respect to origin, it's this. Again, you can use this idea. I mean, if the reflection of a point with respect to y-axis, the origin is here, let's say, if it is on the graph again, and if this is true for all points, so take a point and look at here, its reflection is also on the graph. We say this origin is symmetric with respect to origin. The curve is, or the graph is symmetric with respect to origin. Or you can say, if you do this, reflect with respect to x-axis, then reflect through y. If you get the same thing here, then it's symmetric with respect to origin. So, or we say it's reflect, you'll get this one. Then reflect, you will get this one. So if it's symmetric with respect to origin, we will get same graph. If we reflect the graph through x-axis and y-axis consecutively. So for example, reflect, you get this one, then reflect, you get this one, and take this one, reflect, you get this one, and reflect, you get this one. You see, when you reflect through the x and y consecutively, you will get the same graph. Now we will see how to test the equations for symmetry. You know, for the if the graph is given to us, then it's easy to check the symmetries. Like for example, this is symmetric with respect to y-axis, and this is symmetric with respect to x-axis. You know, so you can check them. You know, if you have graph. But the question here is how to test the graph of an equation. For symmetry. If I mean without plotting the graph, without sketching the graph. So this is the idea, like you know, we have y equal to x squared, for example. So if you plot the graph or sketch the graph, you will have this one, and you say this is symmetric with respect to y. But assume you're not given this, assume you don't have, how can you tell is it symmetric? I mean, is its graph symmetric or not? With respect to x-axis or y-axis. So this is the idea. I mean, this is the question here. Without graphing, can we tell if the equation gives a symmetric graph? Now here are the criteria. Okay, testing the symmetry with respect to the x-axis. If you want to test this one, the symmetry with respect to the x-axis, then you will replace y with minus y in the equation, and if the new equation is equivalent to the original equation, then we say it's symmetric with respect to x-axis. Now when testing the symmetry with respect to the y-axis, then we replace x with minus x in the equation, and we get a new equation. If the new equation is equivalent to the original equation, it is symmetric with respect to the y-axis. Now how to test the symmetry with respect to the origin? We replace the x with minus x and y with minus y at the same time in the equation. At the same time, okay? Then the new equation, if the new equation is equivalent to original equation, then it's symmetric with respect to origin. That's important. And you might ask this question: how to see an equation is equivalent to the other equation? So we say the new equation is equivalent to original equation. Now to see if two equations are equivalent, isolate x term or y term in both equations, then check if you get the equal terms on the other side of both equations. Okay, I will show you this one in the next example. Let's look at this example. So determine what type of symmetry if exists. Okay, if N means if it exists. If there is a symmetry, find it. The graphs of equation exhibit. So what type of symmetry, if any, the graphs of the equations exhibit. Exhibit means show here, show. Now this is the first equation, this is the second equation, and we don't know their graphs, right? We don't know their graphs. Now so we cannot, we don't know the graphs of them, so we cannot tell from the graphs. So we have to use our method, our tests. Now for okay, let's check this one for the, let's check for the first equation for the symmetries. Let's take the original one. This is the original equation. And then if you're testing for y, so you will replace x with minus x in the original equation. So then when you replace x with minus x, you see it's instead of x you put minus x, and then you find another equation. This is the new equation. Now in the new equation, you see the original equation and new equation, they are same. So y cubed is equal to x squared plus 1. Y cubed is equal to x squared plus 1. So they give both the same thing, like y cubed, x squared plus 1. So they are equivalent, or they are same, you can say. Then what does this mean? This means it is symmetric with respect to y-axis. Now let's look at the other test. Now let's test for x-axis. So you remember that for the when testing for the symmetry for the x-axis, you replace y with negative y in the original equation. The original equation is this. So you put here y, negative y, and then we get minus y cubed equal to x squared plus 1. Now how can you check them? Okay, you try to make this one also same with this one. So you multiply both sides with minus. So you multiply both sides with minus. So you minus. It's minus here. So you see now it's y cubed. And y cubed, same thing. But are they same? Yeah, these are same, but they're not same. So we say they're not same and not equivalent. So you see, we didn't get, like, the y cubes are same, but these are not same. If they're equivalent, they have to give the same equation for the same term variable. So then what we say is the test fails here. The test for the x-axis, it fails, so there's no symmetry for the x-axis. Now for the other one, okay, I will put this again. The original equation is this one. The equation is this one. The original equation is this. Now the third one is replace x with minus x and y with minus y at the same time. So you see here y minus y, so x minus x, and then we keep doing that. Okay, we get this one, but to compare them, I need to make this y cubed. So how can I make this y cubed? Multiply both sides with minus, you will get y cubed. And after you do this one, you will get this equation. Now look at here, they are same here, y cubes are same, so we make these y cubes same, isolated this term, but the other terms on the other side not same. So you see they're same. Now these are not same. So not equivalent. The equations are not equivalent equations, not same or not equivalent equations. So for this reason the test fails. So the test fails, so we say it fails. So we say the graph of y cubed equal to x cubed plus x squared plus 1 is symmetric with respect to y-axis only. And let's do part B. Okay, we will check the equation. This is the original equation. Now test for y-axis, so replace x with minus x. Use okay, this is the original one, and then you replace with minus x. Okay, x with minus x we replace. Then what happens is this. So you can isolate x by multiplying both sides with minus x. So let me tell you which one is the new equation. So this is the original equation. This is the original equation. It's this. This is the original equation. Now you replace with x, x with negative x. So this is the new equation. Now you change this equation to x equal to something, because in the original one we have x, we want to do it x. So we multiply both sides with minus. So we will end up with this, again, new equation. Now, now the question is, so this is the new equation, Now we check them. This x are same, no problem, but here y, the absolute value of y and negative absolute value not same. So we say they are not equivalent. So the test fails for y-axis. Now for the x-axis, we replace y with minus y. So here you replace y with minus y. So this is the new equation now, Now a property of the absolute value is this, as you know. So this is a property of the absolute value. So we will get this one. So new equation turns out to be x equal to absolute value y, and which is the original equation. So they are same now. Same equations. We got the same equations. So we say test works. So we get the symmetry for the x-axis. So it verifies the symmetry. It shows the symmetry because we have the new equation is all same as the original equation. Now let's check for the origin. You replace x with minus x, y with minus y. So here you change them like with minus x with minus y. So this is the new equation. Now new equation is this. Now try to make it look like x here. So how can you do it? You multiply both sides with x, so minus. So what do you get at the end? So after doing this, you will get this one. Okay, why it happened like this? Again, I'm telling you, we have this equality. This is the property of absolute value. And then after this, we get this one by multiplying. So you got this absolute value minus absolute value is x. So this is how we get it. And then the new equation turns out to be in this form, new equation. Now the good thing is x, we got x and x, we can compare the other sides. So let's compare the other sides. Let's compare this x, yes. So what about this absolute value y and this negative absolute value y? So they're not same. So not same. So we say they're not equivalent. So the test fails. So for all the tests, only test for x-axis symmetry works. So we say the graph of the equation x equal to absolute value y is symmetric with respect to the x-axis. Now we can use intercepts and symmetry as a graphing aid. So aid means help. So it might help knowing the symmetry and the intercepts might help us to graph the equation. Now here's how to apply it. So it says test the equation y equal to x cubed for symmetry and graph the equation. Let's make the test first. Okay, we will test it for three symmetries. One is y-axis, so you know it's x replaced with minus x. So this is the original equation. And x with minus x. And this is the new equation, right? New equation. And it turns out to be y equal to minus x and x cubed. And this, they're not same. So we say the test fails here. So then the test fails. Now test for x-axis. So you replace y with minus y. Then you get the new equation here. And then you isolate y here, so you want to look them same. Okay, so make them same. So for this you multiply with minus, so you get this minus here. You see minus y equals minus x cubed. So you multiply both sides with minus, and you get this one. Now we want to do this because we want to make them same on these sides, and then check. Are they same? So this part same, but not this part. So it fails. The test fails. Now let's look at the other one, the testing for origin. Replace x with minus x, y with minus x. So here we replace y with minus y, x with minus x. So this is the new equation. Now we have, okay, we will have this one. How? Because you will try to do this, minus y equal to minus x cubed, and we want to get y here. So to get y, you multiply both sides with minus, and you end up with y equal to x cubed. So as you see, they are same, and this parts are same. So it means we got the same equation. same, same. So the test works here. So there's a symmetry with respect to origin. So you say the graph of the equation y equal to x cubed is symmetric with respect to the origin. So what does this mean? This means if you take any point on the graph, like for example, if it is something like that, you can fold it, you can reflect through the x-axis, then y-axis, so you will get the other part. So we will see how to apply it. Now the finding intercepts, we know how to find the intercepts. For the y-intercept you set equal to 0, and for the x-intercept you let y equal to 0, then solve the equations. Like this is y equal to x cubed, the original equation. Put 0, what do you get for y? You get 0, so 0 is the y-intercept. And substitute y equal to 0 in here, so it means you get 0 equal to x cubed. Okay, x cubed is equal to 0 means x equal to 0, so this will be y-intercept. So interestingly, y-intercept and x-intercept turn out to be 0. So it passes through 0 on the y-axis, on the x-axis, like that. So we have such situations: 0, 0 on the both sides. I mean, both on the y-axis and on this. So it passes through the origin. So you see that they give the same point 0, 0. And now next thing is find several pairs of coordinates that make the equation true. So you pick some points. Generally what we pick is how big is this? I pick 1, I put here, so you got 1 cubed, so you say y is equal to 1 cubed, it's 1, so you put it here. And for 2, do the same thing. Put 2 here, you got 2 cubed, y is equal to 2 cubed, y is equal to 8, so you put it here. You will use the relation between y and x. It's this here, y is equal to x cubed. I mean, this is an equal sign, not approximate value, so this is equal. And then we have additional points. Now we can also check so we have some additional point due to symmetry. What we mean here is, if this 1, 1 is on the graph, then -1, -1 is on the graph. This is due to symmetry with respect to origin. So if 2, 8 is there, -2, 8, -2, -8 should be there. Then we can make the graph. So plot the points on the graph. Okay, for now, don't think about this part. Okay, assume you don't know this part. You put the values here. I mean, when you put all the points here, you will get such graph. So think about this also. If you fold it this way and then reflect it to this way, you will get this part. And if you do the same thing like that, you will get this part. You see, it's a symmetric with respect to origin means this. It's symmetric with respect to origin. It means fold it with respect to x, so I reflect it, then reflect it with respect to y. Then you will get the point, another point on the x on the graph. And if you take this one, if you take this part, reflect with respect to x, then reflect with respect to y, you will get the other side of the graph. And okay, as a summary, when testing for all four symmetries, for all symmetries about the x-axis, y-axis, and the origin, there are 5 possibilities. 1, there will be no symmetry, so it means no symmetry for x-axis, for y, and for origin. Or symmetry to x-axis only, symmetry with respect to y-axis only, with respect to origin only, and symmetry with respect to all of them. So what does this mean? So how about this, like x-axis, x and y together? Isn't it possible? No. The important fact is this: a graph possessing 2 types of symmetry works also the 3rd type. So it means if you have symmetry with respect to x-axis, you have the symmetry for the x-axis symmetry plus y-axis symmetry. If you have both, so it means you automatically you have origin symmetry. And any two of them, like y-axis gives the origin symmetry, or take x-axis and plus the origin symmetry, so it gives you the y axis symmetry. So in summary, you get all symmetries together or only one of them. No two symmetry. No two symmetry. It means 2 symmetry means 3 symmetry. Okay, 2 symmetry means 3 symmetry. This is the case. Okay, thanks for watching. Please try to understand. You can test, you can make some graphs and try to get some idea about the graphs of the functions. Okay, thanks for watching.